Okay, let's have a quick look at what happens when we start with the energy, total mechanical energy, being greater than the step height. So that corresponds to the situation here. We have our step potential of height u naught, and we have our total energy that's greater than that, and the particle again is incident from the left. Okay, so if we, in this situation, the reflection coefficient is equal to k1 minus k2 divided by k1 plus k2 squared. If we replace that with the expressions of k1 and k2 in terms of energy and the step height, we get we get this expression, okay, squared. And this is again in general not zero, okay? It's in general not zero. And so it's only zero when u naught is equal to zero, okay? But if u naught is equal to zero, we don't have a step, and so of course there's no reflection, okay? But if u naught is equal to anything not different from zero, then we do get a reflection. And in particular, it's really interesting to note that when you that if the particle was incident from the right with the same energy greater than u naught, or equivalently if it was incident from the left but we had a step down potential, okay, one way to visualize that would be if we just kept everything the same, but instead of u naught being positive, it was negative. So if we had a potential that looked like that, okay, minus u naught, then we would replace u naught with minus u naught, okay, and so these two terms would be different, but nonetheless, since there's a square here, we would still get a reflection coefficient which is different from zero. And this is really interesting. So this means that the particle coming to a region where in fact it would classically be accelerated to the right. So if it's coming from the left, from left to right, and it's classically when it gets to this potential, it's like rolling down a hill. Again, since f is equal to minus du dx at this position here with this step down potential, we df dx du dx is negative, and so the force is positive. So classically the particle will get accelerated to the right, and here, despite that, quantum mechanics says that the particle has some probability of getting reflected back to the left. So this analysis shows that that we have that the particle can get reflected even with a step down potential, which is obviously far deviates pretty drastically from the classical prediction. Okay, I just realized that I made a mistake throughout this whole lecture in my definition of K1 and K2. Okay, so back here, I defined K1 to be the square root of 2me over h bar. The h bar and K2 is equal to 2me minus u naught over h bar. These h bars do not belong under the square root. Okay, and so they should be written like this and like that. Those are correct. So these expressions for K1 and K2 are now correct. Okay, so with that, then we find that when E is less than u naught, then for x is greater than 0, then K2 is going to be the square root of a negative number because E is less than u naught. So this is negative. So if we multiply this by -1 so that we can rearrange it, then we have the square root of -1 or I outside. Okay, and so we get this, and now we know that the wave function in the region x greater than 0 is equal to c e to the I k2x, which is equal to now c e to the I times I alpha times x, where now we've set this quantity here equal to alpha, and that is equal to c e to the minus alpha x, and so we see we have an exponentially decaying function, and this is called an evanescent wave. Anytime you have an exponentially decaying wave function, we call that an evanescent wave.